everyone.
Hello? Hello? Okay. Got it. Thank you.
Thanks for coming our talk. My name is Mu Huan, and this is my colleague Dee. Both of us are PhD students at UCLA. And at this moment, we are part-time working at the Falcon Computing Solutions. This talk is about deploying accelerators at data center scale using Spark. And this presentation, you'll see how to get 3x speed up for your Spark applications by using accelerators, and how you can do it within 3 hours. And in this talk, we're going to explain to you what are the challenges we have encountered, how do we solve these problems, and most importantly, we are talking about what we provide so that when you come to this topic, you don't have to go through all these painful processes that we did. Today, we are going to talk about accelerators in data centers. The reason that we are looking at this topic is that we have seen that CPU core scaling is coming to an end. And using multi-cores and increasing number of cores isn't bring you too much power performance efficiency. And we see data center demand new technologies to sustain scaling. And we have seen accelerators are gaining popularity in this area. GPU is popular, FPGA is gaining popularity, and recently Google unveils its TensorFlow computing unit. It's a specialized ASIC to help accelerating machine learning applications. And in the FPGA era, recently we have seen that Microsoft Bing Searching is adopting FPGAs to accelerate the search engine, and IBM is using FPGAs to accelerate the non-SQL query. We have seen news announcement that Altera and IBM are collaborating to accelerate the search. And last year, Intel acquired Altera. By the way, Altera is an FPGA company. And Intel is predicting that by 2020, 30% of data center nodes will be equipped with FPGAs. So that's why we are looking into this area. Before we go deep into this topic, please allow me to introduce a little bit about us. We are working at the UCLA Center for Domain-Specific Computing. It's founded in 2009 under the Expeditions in Computing program from NSF. And in 2014, we received funds from public-private partnership between NSF and Intel. Falcon Computing Solutions is a spin-off company from the CDSC Center. It is founded in 2014. The vision of the company is to enable customized computing for big data applications. For those of you who are not familiar with FPGAs, FPGA stands for Field Programmable Gate Array. It is a reconfigurable hardware, and it has millions of logics on chip so that you can customize it to accelerate specific computations. FPGAs are typically integrated into servers by 2 ways. One is through PCIe bus. An example is the IBM Capi platform. The other way is to put FPGAs in the CPU socket. And an example is Intel Hub platform. There are many benefits of FPGAs. First, it's very low power. It consumes 20 watts per board. And it's energy efficient. It can provide customized, high performance. With all this aside, we still see problems of deploying accelerators in data center efficiently. Let me explain the challenges we have been through. First, programming model is complicated. Not every software understands how to program FPGA or GPUs. And it requires too much hardware-specific knowledge to use these accelerators. You don't need to write a bunch of glue code so that you can offload your computation to accelerators. And another problem is that it lacks a platform portability. When you switch your accelerators from FPGAs to GPU, you need to rewrite these gluing code. The second challenge is about JVM to accelerator data transfer overheads. Spark is usually running in the JVM, and accelerators usually are peripheral devices. And you need to transfer your data from JVM to accelerators. And during this process, we need to do data serialization and deserialization. We need to serialize data so that the data object can be serialized into a byte array, and which can be then transferred to accelerators. And the results from the accelerator need to be deserialized so that it can be continued to be used in the Spark program. And this additional data transfer also may hurt your performance. In the data center, we are thinking there are 3 groups of people. Big data application developer, who is a software developer and knows all about the Spark. And there are another bunch of people called accelerator developers. They are hardware engineer and know all the hardware specific knowledge. And also we have system administrator. Everyone's busy and you don't see them that often. So the communication is actually quite time consuming. When accelerator developer has an accelerator ready, it asks, is my accelerator working? Can it fit in your data center? What's the platform in the data center? When software engineers want to use this accelerator, it will ask, how can I offload the computation to your accelerator? What's the I/O interface? And when he wants to run the application, he asks, which class of nodes has accelerators? And here we are trying to see, is there any way that we can define a unified APIs so that communication is going to be much easier? Finally, there are more challenges for FPGAs. The reason is that reconfiguration time is pretty long. Believe it or not, reconfiguration on FPGAs takes about ½ second to 2 seconds. During this process, the executable binary needs to be transferred to the FPGA device, and we need to reset all the bits and vowels on the FPGAs. And in our experiments, we have seen that naive runtime FPGA sharing may slow down the performance by almost 4x. So what we did, first we are going to provide a better programming model. We provide a set of APIs for accelerator developers. And these APIs enables easier integration for accelerators into the big data workload. And by using these APIs, we make sure that your accelerators is compatible to the whole ecosystem. Second, we are providing APIs for big data application developers. By using these APIs, you can use, you get to know how to do the data transfer between applications and accelerators. And we no longer require any hardware knowledge for the software programmer. The benefit of these 2 sets of APIs is that we want to decouple the accelerator developer from software developer. Second, we are providing an accelerator management in runtime. This runtime currently supports both FPGAs and GPUs. We'll get to that in a minute. So we call this system called Blaze. It's a system providing Accelerator-as-a-Service. Before I talk how our system fits in the whole system, let's first take a look at the YON today. A typical YON setup including one resource manager and a few node managers, which is RM and NM in this graph. And usually each node manager manages the whole resource on a CPU node. And this node manager talks to the resource manager to report the resource and node status. When a client wants to run the application, it first submits a package to the resource manager, and then an application master will be launched on this cluster. Application master manages the whole computation and all the tasks for this application. Application master will send resource requests to the resource manager, and new containers for computation will be launched on the node. In this case, we are seeing 2 containers launched on 1 node. And these containers will be executing the CPU softwares inside. In our Blaze, in our accelerator runtime system, we first add a new set of accelerators. We had a GPU and FPGA platform attached to each node. And we provide 2 processes. First, we provide a component called NAM. It's short for Node Accelerator Manager. This handles local accelerator service management, handles all the data transfer between CPU and accelerators. And then sitting inside YON, we also have a global accelerator manager. This global accelerator manager oversees all the accelerators in this data center. At this moment, GAM is attached to the Apache YON, and Node Manager is a standalone C process. With all this, I'll hand it to Dee, who will finish the rest of the presentation.
Okay, so I'm going to talk more on the details about the programming interface and the runtime implementation of Blaze. So first, I will go through the interface, the application interface for Spark. So here I show a simple example of logistic regression training. We have RDD storing the data points loaded from the disk. So these are the training data samples. And then in each iteration, we calculate the gradient from these training samples. Because we're going to reuse the data samples, we can indicate the Spark that we want to cache this points RDD. And also, because the main computation of this application is a gradient calculation, we want to use the accelerator to accelerate this gradient calculation to make the whole application faster. So in order to do that, we only need, using the Blaze API, we only need to identify the RDD that needs to be accelerated. So we use a wrap around the existing RDD, and that wrapper, after the wrapping, the generated RDD will be an acceleratable RDD, or short for ACC RDD. And the next part is that we need to use a customized RDD transform function that can be defined as an extension of a provided base class called accelerators. So in this extended function, we only need to define the ID or the name for the accelerator. So this will be a name of that accelerator service, in this case, a logistic gradient calculation. And under the hood, what this does is that when we call the wrapper, we generate a new extended RDD called ACC RDD. And in the ACC RDD, we extend that compute function to provide a set of operations to serialize the data, send the data to the accelerator node manager. And after the accelerator is finished, we get a result and deserialize and send it back to the Spark task. Similarly, we have a set of API for accelerator developers. So I'm not going to go into details about this, but the idea is very similar, is that we provide the base class for each accelerator, and then the accelerator developer only need to override this compute function, and then so that they don't need to worry about the application details, don't need to worry about how to get the data from the applications. They only need to get the, so the accelerator invocation will be handled by the runtime system. And for the deployment interface, we leverage the existing label management in Yarn to manage accelerators as services. So this Yarn support for labels are in this 796 discussion thread, so you can have a quick look if you want to know more details. So putting it all together, the runtime deployment flow looks something like this. So first, when the accelerator developer had developed this acceleratable task or the accelerator implementation, we have an interface to register these accelerators on the corresponding data center nodes. And after the accelerator are registered, the information of the accelerator will be propagated from them to the global accelerator manager. So then when the user requests the corresponding accelerator using this ACC ID, the global accelerator manager will allocate the correct nodes in the data center that have the matching accelerators and allocate the containers to the user application, and then propagate some container information to each node to the node accelerator manager. And then the user application can start the accelerator invocation and start offloading the computation. So now I'm going to talk a little bit more details on the implementation of the runtime. So the key of providing accelerator as a service is achieved by separating logical accelerators and physical accelerators. So here, logical accelerators indicates the accelerator functionalities. For example, we have logistic gradient calculation, we have k-means calculation, for example. And the physical accelerators correspond to the specific implementation on the physical device. For example, we can have FPGA implementation of the logistic gradient calculation, GPU implementation for the same calculation, and so then the idea is that the physical and logical accelerator can be decoupled such that the logical accelerators will be exposed to the application developer, and the physical accelerators will be exposed to the accelerator developers. And then in the middle, the runtime system have a bunch of queues, both logical queues and physical queues, and a set of schedulers to operate this whole task scheduling, so that both ends the developer does not need to have specific information for one another. So next part, I'm going to briefly talk about the techniques we used to optimize a JVM to accelerator data transfer. So first is the traditional double buffering. So we pipeline the task, we pipeline the deserialization transfer with accelerator execution. And in addition to that, we also provide accelerator sharing. So multiple applications, multiple jobs can use the same accelerator. So then their computation can be overlapped with each other to boost the accelerator utilization. The second part is data caching. So we leverage the in-memory caching provided by Spark so that we can further cache the reusable RDD in the accelerator device memory. And finally, we also provide a broadcast similar to the Spark broadcast. The basic idea is if multiple tasks share the same data, the data only need to be transferred to the accelerator once, and the tasks are able to share all those shared variables. And so for the next part, I'm going to talk about how do we optimize this FPGA reprogramming overheads. We optimize that on the global FPGA allocation level. So the key idea is just we want to avoid FPGA reprogramming as much as possible. So just show an example here is a bad allocation. So when we have 4 applications requesting 2 types of accelerators, if the applications requesting different types of accelerators got allocated on the same node, they're going to compete the FPGA resource, and then the FPGA resource, the FPGA chip, need to be reprogrammed to serving 2 different kinds of accelerators, logical accelerators. So then a better allocation is simply localize the application requesting one type of accelerator on different nodes. And the important part is that because the workload is changing dynamically, the global accelerator manager needs to make such decision dynamically with some information on the application. So next, I'm going to briefly talk about the evaluation of Blaze. First, I show a very naive programming effort reduction illustration. Here, we show the lines of code reduction of the accelerator management. So this part does not include the changes in the application or the necessary code you need to control the accelerators, because usually those part is a one-time deal. You only need to program your accelerator once and then let people use it. But this part is really more difficult because in the current accelerator programming model, you need to have both all the informations with application, accelerator programming, as well as some system administration. So then, although the code might not seem to be a lot, it is very difficult for big data programmers to do this. But the Blaze, what we do is we want to reduce that, and we want to eliminate that and provide a general runtime. And these workloads are what we have at UCLA as well as Falcon Computing. This is general compute intensive workloads. And at both UCLA CDSC and Falcon, we have the small scale clusters that is equipped with both low power GPUs and FPGAs, so that these accelerators is the form factor led them to fit in the commodity servers, and we have a bunch of them. And we can do evaluations on different workloads, including genomic sequencing and machine learning. So here is very simple results on the overall system performance and energy efficiency achieved. In general, we achieved 1.7x speedup to 3.2x speedup, and 1.5 to 2.8x energy reduction. So finally, let me show a quick demo. So these are, this will be a demo executed on Amazon EC2. We requested 4 instances, and 2 instances with CPU and 2 instances with GPU. So this is a short video we recorded a couple days ago to make it smoother. So here we show a normal Hadoop Yarn cluster management GUI. And then, sorry, just pause it real quick. And then in this node statistic, we show that there are 4 nodes. And then the 2 nodes that have GPU, we assigned a label on them. This is NVIDIA GPU with OpenCL runtime. And then just to mention a little bit, these two nodes are, one of them has 1 GPU, and the other has 4 GPU. So one of them is a 2x GPU instance, and the other one is an 8x instance. We're going to show with the runtime system, the application does not need to be aware of such heterogeneous configuration of the nodes. So so these node labels are propagated by the node manager running on these two GPU nodes. And we added another accelerator page showing all the available logical accelerators in the data center on our cluster, as well as their devices. So we have logistic gradient and k-means contribute calculation on the GPU. So now we're going into the terminal, and we're going to start launching some Spark job to the cluster. So first, I will show a Spark Summit script for the CPU. So this will be a normal Spark Summit script. This is traditional with nothing changed, with some binary logistic .jar. And then we launch it to the Yarn cluster, and we can see in the GUI the management, the resource manager received the request, and then the request will be accepted, and then launched on 2 of the CPU nodes. So in this node page, we can see that the containers as well as the application master are launched on the CPU nodes. And then when the computation finish, we can see this is a small data set. The computation finishes in about 1.5 minutes. So now let's look at the script to launch it, the same application, the same JR file, but with accelerators. So in the script, the only thing changes is this line to assign a label to the Spark Summit script. We assign this logistic gradient label to it, so that this job needs a logistic gradient calculation accelerator. And then when we launch this new script, we also start a script to monitor the GPU utilization using this NVIDIA driver call. And then you can see this new accelerator equipped logistic application is accepted. And then the container, the executors, Spark executors are launched on the nodes with GPU accelerators. And when the job finishes, you can see it finishes in a little more than 30 seconds. So that's the 3x speed up we talked about. And now let's look at the GPU utilization plot. We have a very simple Python script to plot that. So first, let's look at the GPU utilization on the first node where there's only 1 GPU. So yeah, on the top, we show that during the execution of the job, the GPU utilization is about 75%. And then we plot the utilization for the 4 GPU nodes. And because this is a very small workload, and then the task number is limited, so then the utilization on the 4 GPUs are a little bit lower because there are not enough workloads there. So for the next part, we're going to show that we're able to share the same accelerators with multiple jobs, such that we can increase the utilization as well as the system performance. So here, we're just going to launch 3 logistic jobs simultaneously. And from the GUI, you can see that all the 3 jobs are accepted by the Yarn manager instantly. Right. And then we can also see that in the node page, all the containers, executor containers, are launched on the GPU nodes. And when the job finishes, you can see all the 3 jobs actually finishes a little bit more than 30 seconds because for each job, they have some time to load the data as well as, so then the accelerated execution can be overlapped with most part of the CPU execution. And then this GPU utilization on the single node is increased to close to 100%. And then this 4 node GPU nodes also has a great boost on the utilization. And with that, I conclude the demo. And then let's go back to final remarks. So the takeaway message is that with careful design runtime system, the accelerator deployment can be made easy. And there are a lot of works on the GPU runtime, but our experience shows that FPGAs require special considerations. And then the key to the efficiency of such system is the JVM-to-ACC overheads, to accelerator overheads. We're looking for new ideas. And also, finally, Blaze is an open source project, and we're looking for collaborations. So let me do a little bit advertisement for Falcon Computing. So the main product of Falcon Computing is surrounded around Blaze in order to provide a better experience for deploying accelerators on Datacenter. So the Falcon has existing accelerator library for deep learning and machine learning, as well as genomic sequencing. And also Falcon has a FPGA, highly optimized FPGA compiler that can transform a software code directly into the FPGA implementation. And then these two parts can be synthesized into Blaze-ready, Blaze-compatible accelerators. And on the runtime, we also have better management and platform support. So finally, we thank our sponsors for support and machine donations. And with that, I conclude the talk, and we're welcome for questions. Thank you. Yeah.
Great presentation. So from the demo, it seemed like Blaze runs on top of OpenCL. For the GPU at least. Is that the case also for the FPGA implementation?
Yes.
If not, what changes do you make to support FPGAs?
Right. So actually, Blaze is compatible with different kinds of runtimes. In this case, because we provide a C++ accelerator interface, so whether you use OpenCL or use CUDA, it can be both supported. And but yeah, to answer your question, we have both OpenCL. We have the OpenCL runtime for both GPU and FPGA. And because OpenCL, although OpenCL has a specification for heterogeneous platform, the vendor implementation of the runtime is slightly different from one another. So for that, we do need to provide different implementations of that. In Blaze, we have this abstraction called platform. So each platform, you can have a platform for OpenCL, platform for OpenCL FPGA, platform for OpenCL GPU. And then those platform implementations, similar to OpenCL, can be loaded at runtime from Blaze as a dynamic library. Yeah.
For your physical accelerators, what compile times are you seeing for the FPGAs, and how often do you recompile?
Right. So this is a big problem of FPGA because FPGA compilation typically takes hours. Usually, they need to be done overnight. So that's the main reason we provide Accelerator-as-a-Service rather than for the GPU case, a lot of the runtime supported just-in-time compilation. So for the FPGA is that you have this accelerator is semi-fixed. You program the accelerator once, and the accelerator can be switched at runtime, but then you don't really resynthesize because every time you resynthesize, it takes a long time. So if your workload gradually, you need to do it offline.
Hi, two questions. First one is what was roughly the amount of data that was being sent to the accelerator in this experiment? And the second question is there a point at which if the data grows so big that either your serialization, deserialization, or the JVM-to-ACC communication, that overhead becomes so much that it's not, you might as well compute everything on CPU?
Right, thank you. That's a great question. So for the first one, you're asking for the demo, is that right? So we're just running a very small data set. This is MNIST contingent recognition. So 60,000 data samples, each with like 700 floating points. So a couple hundred megabytes. And the second question, part of that is really related to the application. For example, if your application is very compute intensive, we see that, for example, deep learning, the computation times is much larger than the data transfer time. For that, if you are accelerating the deep learning, the convolutional neural network on the GPU, the benefit of getting it accelerated outweighs the data transfer. But for a lot of workload, like this logistic regression and k-means, this is like a in-between kind of scenario. So in some cases, if the data is very, very large, such that it cannot fit in the memory or the accelerator device memory, then we see a pretty big overhead in the data transfer. Yeah, so then I think the question is really what kind of accelerators you provide. So for those that the non-computation intensive, those are better integrated, better executed on the CPU. Yeah.
Question here.
Where? Oh, okay.
So why is 2x speed up good enough to move to accelerators rather than scaling up the number of computing nodes?
Are you asking the trade-off between CPU and accelerators? So I think part of the motivation for this part, for our research, is that the scaling of the CPU is coming to an end. So then when it's coming to an end, and then the demand for data center keep growing, there's a limit on the amount of computation you can provide in the data center, typically limited by the energy. So then there's really this, we need to seek of a new techniques such as like the customized accelerators to sustain this scaling. Yeah. Okay.
Yeah, so the current implementation, is it specific to the Intel platform? If yes, how much time it takes to, for example, port it to IBM Power 8 or something like that, you know?
Right. So the question is that what's the effort of doing this platform support on different types of accelerator platform? So like I said in the earlier comments, is that the Blaze, aside from this accelerator implementation API, also has a platform API. So all you need to do to support, for example, like the Intel AAL runtime to support the Intel HARP in-socket system, you only need to wrap the AAL APIs with APIs of the Blaze platform. And then you want to, in the platform, we define some physical queues and then the scheduling for that. Similarly for IBM CAPI. So I think if not now, or maybe in the near future, IBM CAPI is going to support OpenCL, right? So then I think the similar techniques in the OpenCL runtime for other type of FPGA can be leveraged. So there's a really little overhead in supporting different platforms. Yeah. Okay. Right, with that, thank you very much. And
Thanks.
then, yeah.